All right, hello everyone. So previously we talked about collisions in one dimension, and we were able to apply these two very powerful principles, conservation of energy and conservation of momentum, which are always true, to derive two general formulas. But those two general formulas weren't enough. Okay, we couldn't solve the problem. We needed to give a third bit of information which tells us something about the nature of the collision. And so there were two very important special cases. So one of those is a perfectly elastic collision in which none of the original kinetic energy is converted into other forms of energy. So kinetic energy initial equals kinetic energy final, which follows from delta E other equals zero and conservation of energy. And then we were able to solve those two equations for the two unknowns, which are the two final velocities of the two objects, little v and big V prime. Okay, and then the other very special and important case is the perfectly inelastic collision. Okay, and so that's where you say that these two objects, they collide together and then they take off, it's a hit and stick, they take off with the same final velocity. And so you could solve this conservation of momentum and conservation of energy to get the final velocity of those two clumped together objects. And in addition, you could calculate how much of the original kinetic energy went into other forms of energy during that collision. Okay? So we consider that in one dimension. In the case of collisions in two dimensions, it's still true, as it is always true, that there's conservation of energy and conservation of momentum. But now in this case, conservation of energy will give you one equation, and conservation of momentum will give you two equations, x and y components. So you have three equations, okay? And so we'll write down conservation of energy, conservation of momentum. But still, that's not enough to solve the problem. You have to give one more piece of information, and again, what emerges is two sort of special but important cases, perfectly elastic collisions, where delta E other equals zero, which is the first example we'll do, and then perfectly inelastic, where the two objects clump together and move off with a common final velocity. And so then you can solve for that, and then you can also solve for how much of the original kinetic energy went into other forms of energy. Okay, so the difference between two collisions in two dimensions and collisions in one dimension is just that in two dimensions there are so many more parameters that it's difficult to write down, or useless to write down sort of general formulas. So basically you just look at any particular collision problem, and you just write down conservation of energy, conservation of momentum, and you provide some additional information, elastic or inelastic usually, and then you just solve the equations. You just write it down and solve them. Okay, so what we're going to do, before we begin, let me just say something in general about collisions in two dimensions between, say, two objects. Okay, so, the most general kind of situation you have is, say, there's some object here coming in with some velocity like this, and there's another object, a second object, coming in with some other velocity, just a random direction, and they collide over here, and then this one bounces off like this and takes off in that direction. This one bounces off like this and takes off in that direction, whatever. So if we focus on the initial condition here, we've got two arbitrary velocities, or two arbitrary momenta. Now, here's where, thinking a little bit about the choice of inertial reference frame is important and helpful. Okay, so for example, you can always choose, if this is the situation in the original inertial reference frame, you can always choose a reference frame which is, say, for example, drifting with exactly the same velocity as this guy, so that from the point of view of someone in this inertial reference frame, this object is at rest. Okay, so this guy sees this object at rest, and he sees this object moving it with some momentum in some direction toward that object. Okay, and then you can make a second choice, which is you can rotate the axes of the coordinate system so that the second object is moving, say, along the x-axis always. So you can choose it like this. This is your x-axis, this is your y-axis, and the second object is moving just along the x-axis. Okay? So by choice of the velocity of the reference frame and the orientation of the reference frame, it is always possible to convert any arbitrary two-dimensional collision between two objects into a situation where one is at rest and the other one is coming in, say, exactly to the right. Okay, and so let's apply that. Let's assume we've applied that idea. And we'll then end up with that kind of situation. And a really good example of that kind of situation in the context of elastic collisions is the game of pool, billiards. Okay, so when you play pool, billiards, sure, it's true that when, say, the cue ball, the white ball, hits a colored ball, there is sound coming off. Okay, and the balls heat up a little bit. But in that game, the amount of sound energy generated, the amount of thermal energy generated, in other words, delta E other, is very small compared to the original kinetic energy in those balls, well, in this ball. And so to a very good approximation, you can just say delta E is equal to 0, or approximately equal to 0. So we'll assume that it's exactly equal to 0, which is a very good approximation for the game of pool. So our situation looks like this. We've got one object that's at rest, which we will take to be the colored ball. So let me put that here. Okay, so we have the colored ball of mass m, which is initially at rest, and then we have the cue ball is coming in, the white ball is coming in, and we'll suppose that the white ball is going to hit the colored ball, not head on, because then the colored ball just takes off that way, but maybe a little bit above or a little bit below, so that the colored ball takes off that way or that way. Okay, so we trace this back, and so the white ball, the cue ball, starts off like this. And so the only real specialization that we're doing in this example is that we're going to assume that the masses of the two objects are equal, which is the case in the game of pool. Okay, the only way we could generalize this 2D elastic collision is to make one of the masses different from the other. Okay, so it's not much of a specialization here. Okay, so then we say, great, this guy's at rest, and the cue ball is coming in with some initial velocity to the right. So really, we just need to specify the magnitude of this initial velocity of the cue ball, and because we know that it's moving to the right by this argument. Okay, so that's our initial setup there. And then the idea is this ball, the cue ball, is going to hit the colored ball, and the colored ball is going to go off at some angle. So after the collision, the colored ball will be here, and the colored ball will be moving with some velocity. Let's call that v. This is v initial, and this is v final. Actually, you know what? Yeah, that's fine. Although, let me just get rid of the ball, because we're going to run out of room here. Okay, so what we've got is this colored ball takes off like this, and it's got some velocity, which we'll call v final prime. Okay, and the angle that it takes off at, relative to the right here, counterclockwise, is an angle alpha. And we are going to choose this angle so that, this is the pool table here, so that this colored ball goes into this pocket. Okay, and then here is the other pocket at this end of the table. Okay, so we've got that. So the cue ball comes in like this, and it strikes above the center of the colored ball. So the colored ball gets directed at an angle alpha, and that angle alpha we know because we want that ball to go into that pocket. But then when the white ball, the cue ball, hits the colored ball, well, it's going to be deflected this way. So when the white ball strikes the colored ball, there'll be forces in this direction. So the colored ball will exert a force on the white ball in that direction over a very short amount of time, and so it will change the velocity in that direction. Okay, so you take this initial velocity, add that velocity, and you get a velocity, say, in that direction. So it deflects off in some direction like this. Okay, so it takes off in some direction beta. Okay, with some final velocity v final. So cue ball has initial velocity v initial, final velocity v final at an angle beta. And the real problem here is that we don't want the cue ball to end up in that pocket. So we want to select this angle alpha here. We want to choose that to be some angle, and then we want to double check that the angle beta won't be such that the white ball ends up in the other pocket, because that's of course a foul shot. Okay, so that's our situation. So now let's think about this a little bit. So what are all the variables in this problem? Well, there's a lot. So there's v initial, the initial speed of the white ball to the right. That's a parameter that we can adjust. And there's the final speed of the white ball or the cue ball, and there's the angle at which it is deflected, beta. We also have the final velocity of the colored ball, so its speed, little vf prime, and its angle, alpha. So we have 5 parameters that are part of this problem. And then we think about this and we say, well, how many equations do we have? Well, we have 3 equations. So there's conservation of energy. So in this case, thought of in the context of the total energy of an isolated system doesn't change. So delta E total is equal to 0. That'll be one equation. We also have conservation of momentum, thought of in the context of the total momentum of an isolated system doesn't change. So delta P total equals 0. This is a vector equation in 2 dimensions, which means that it's 2 equations. So we have 3 equations, and we are going to, but we have 5 variables. So we are able to select 2 of those as known and then solve for 3 of them. So in this case, it's kind of obvious. Well, we would like to specify the initial speed of the cue ball, how hard we hit it. So let's say that this one here is known. We'll indicate with a check mark. And we'll suppose that we need to know, or we're going to specify the angle alpha that we want the colored ball to take off at so that it goes into that bottom right pocket. So we will suppose that we will specify those 2. And then we have 3 equations, and we can solve for these 3 unknowns. The final speeds of the white ball and the colored ball, and the angle at which the white ball takes off. And then we're going to ensure that that angle is such that the white ball doesn't go in that pocket. So this is what we're going to solve for. Okay, but remember that when we're trying to solve for that, the conservation of energy equation introduces sort of a new wildcard. And so we have to give an additional piece of information, and in this case we're going to specify that it's elastic collision, which means delta E other, and that's the other bit of information. And then we really have 3 equations in 5 unknowns, and so we give 3 equations in 5 variables. We choose 2 of them as known, and then we can solve for the other 3. Okay, very good. So let's apply first conservation of momentum in the form that the total momentum of this isolated system doesn't change. So there are no forces acting on these 2, on the white ball and the colored ball, except the forces of collision, forces internal to that system. Okay? Okay, so we say conservation of momentum reads this. 0 is the change in the total momentum. Okay? And so that's total momentum final minus total momentum initial is equal to 0. So P total final minus P total initial. Okay, so let's just write those out. So P total final. In the final situation, what do we have? We have an object of mass little m moving with a final velocity v final. That's the white ball. Plus a colored ball of mass m moving with velocity vf prime. Okay, that's the final total momentum. Subtract the initial total momentum in the system. Well, this one is not in motion, but the white ball, the cue ball, is, and it has mass m, and it's moving with an initial velocity v initial, which we've specified as being to the right. Okay, so the sum of these things has to equal 0. So one thing that's nice is because these 2 masses are the same, we can just cancel all the masses, because this 0 equals this. We can just divide both sides of the equation by m, and that cancels out. So this just says that v initial is equal to v final plus v final prime. So conservation of momentum in this case, conservation of momentum is always, p initial. In this situation would be p initial is equal to p final plus p final prime, but because the masses are equal, it just involves v initial is equal to v final plus v final prime. So v final plus v final prime is equal to v initial. Okay, and then this is 2 equations. And what we could do is we could split this into x and y components. Say choose x to be in this direction and y to be in this direction. So this is, I hat and this is j hat. And we could split the initial and final momentum into x and y components like that. Or it's much simpler and clearer to see sort of physically what's happening in this really simple situation to draw a triangle. Okay, so this is a triangle. Okay, and so we can represent that as a triangle is what I mean to say. Okay, so let's do that. So this is so it's saying that V initial, so V initial is this guy. So it's it'll be the base of the triangle here. So that V initial is equal to V final plus V final prime. So V final is this one, so we add these vectors tip to tail. So we say this is V final, and we add to that V final prime. So that's V final prime. So V final plus V final prime added tip to tail has to equal V initial, and so we have this simple triangle. Okay, and then let's look. What in this triangle is known and what is unknown? Well, we know the length of the base of the triangle. Let's put in the angles here first of all, sorry. So V final prime, which is this guy, is taking off at an angle alpha below the horizontal, below that. And so this angle in the triangle is identified as alpha, which is the angle that we're going to be given. And then VF goes off at an angle beta relative to the horizontal. So this angle here is beta. And we'll label this angle, the third angle, gamma. And of course we know that gamma is equal to, let's write it this way. We know that alpha plus beta plus gamma is equal to 180 degrees, or pi radians. Okay, so we have that. And then so what do we know about this? Well, what we know is the base of this triangle. Let me just put it down here. We know the side length of the base of this triangle. That's the initial speed. And we also know the angle alpha. This angle alpha. Now the thing about a triangle is if you know 3 pieces of information about the triangle is entirely determined. So what we need to do is we just need one more bit of information. If we knew, so we need one more bit of information about the triangle. That could be the unknown V final, or it could be the unknown beta, or it could be the unknown V final prime. Okay, and so you can see this easily. For instance, suppose we gave this side length the magnitude of V final prime. If we gave that, we would know how far to extend this line, and then the entire triangle is determined. Or suppose we gave the angle beta. Okay, so then we know the angle beta. Okay, it's a given angle like this, or it's a known angle like this, is then it will intersect with that line, and then the entire triangle is determined. And similarly, if we gave the side length, this side length, V final. So what we need is basically one more equation. So the conservation momentum gave us 2 equations, okay, and we need one more equation, and then that will determine all sides of the triangle, and we can solve for the 2 final velocities, 2 final speeds, and the angle beta. Okay, so we need one more equation, and then the triangle is completely determined, and everything is known. And that one more equation, of course, is conservation of energy, which is always true. Okay, so conservation of energy is going to take this form. So we're going to say 0 is equal to the change in the total energy in an isolated system. Okay, and so the kinds of energies involved in this this process of collision, well, obviously there could in principle be changes in kinetic energy, and there could in principle be thermal energy generated, sound energy generated, and everything else. So it's delta kinetic plus delta E other. And the sum of those two has to equal 0. And now, so this wouldn't be enough. We need to somehow say something more about this, because this delta E other is kind of like a bit of a wild card here. And so what we do is we say delta E other is equal to 0. Okay, so we're saying that this thing is equal to 0. Okay, and so that tells us that conservation of energy tells us that when we say delta E other equals 0, then the change in the kinetic energy is equal to 0. Okay, so then we can write that down. So that's the form that conservation of energy takes. So 0 is equal to the change in the kinetic energy. Okay, so that's kinetic energy final minus kinetic energy initial. So in the final situation, we have two balls in motion, each of mass little m. So there's a 1/2 little m. One of them is moving with a speed vf squared, plus we have the colored ball of the same mass moving with a speed vf prime squared. That's the final kinetic energy in the situation. The initial kinetic energy in the situation is just we have a ball of mass little m, the white ball, moving with an initial speed v initial, and then we square that. Okay, so we get that. And now it's the same thing. Because we've made this simplification that the two masses are equal, rather than being a relationship between, P final squared and P final prime squared and P initial squared, it just becomes a relationship between the squares of the velocities, because you can divide the entire thing by 1/2 m. So the 1/2 m cancels out everywhere. And so we get this simple relationship. Conservation of energy in this case, with this additional condition that we're putting in, tells us that V initial squared is equal to V final squared plus V final prime squared. Okay, so that's that. But now we look at this and we say, let's look back at this triangle. So this kind of looks like a Pythagoras kind of a relationship, right? It's saying this side squared is equal to this side squared plus this side squared. So if you remember something about triangles, you know that that's going to mean that this angle here is 90 degrees. Okay, it's a right angled triangle. Okay, so if we look at the triangle in general, so this is still a general triangle here. We haven't yet applied this condition here. Let's just circle it. Okay, we haven't applied that condition yet. But a general triangle, or for a general triangle, we can say, instead of, we can apply the cosine rule. So the cosine rule says that this side squared, this is a general rule, V initial squared, is equal to V final squared plus V final prime squared, the sum of the other two sides squared, minus twice V final prime times cosine of the angle opposite this V initial side. Okay, and so that's gamma. Okay, so this is true in general about a triangle. This is what conservation of energy tells us. And so we look, we just match all the terms and we say, it must be that this term is equal to 0. Okay, and so if that term is equal to 0, these two final speeds are in general not 0. And so we require cosine of gamma equal to 0, which tells us, so cos gamma equals 0 tells us that gamma is equal to 90 degrees. Okay, and so it tells us that we're dealing with a right-angled triangle. Okay, so what that means is if gamma is 90 degrees, then we have 180 minus 90, so we have alpha plus beta is equal to 90 degrees. So it tells us that the angle alpha plus beta is equal to 90 degrees. So that's an interesting result. So what it tells you is that in this situation, like in a billiard ball situation, to the extent that this is true as a good approximation, it will always be true that no matter what angle alpha you choose here, the angle beta will be such that alpha plus beta is 90 degrees. Okay, so they take off like this. Here's 90 degrees. Okay, so no matter what you choose alpha to be, beta is immediately determined to be 90 degrees from that. Okay, so that's kind of cool. That's an important sort of thing to observe about this. So in other words, if you know alpha, which we do know, we're specifying alpha, then immediately beta is known. So beta is just 90 degrees minus alpha. Okay? And so then when we look at our triangle here, our triangle looks like this. There's the base of it is of known magnitude, length V initial. There's an angle here, alpha, which is known. And these side lengths are such that this is exactly 90 degrees. Okay, so there's an angle beta here. And this is v final, a side of length final speed, and then a side of length v final prime, final speed prime. So that's what our situation looks like. Okay, and so then we can immediately write down the answer. So we know the answer for the angle beta, it's just 90 minus alpha. Now we just need these two final speeds. And from this triangle, you can just immediately write it down. So the final speed of the white ball, the cue ball, well, that's going to be equal to the initial speed times cosine of beta. So that's v initial times cosine of beta. But because beta is 90 minus alpha, that's the same as sine of alpha. So that's v initial sine alpha. And v final prime, so that's the final speed for the colored ball. That thing is the side length there, which is going to just v initial times cosine of alpha. Okay. And we're done. And so you can just double check. I mean, if I take this thing squared, v final squared plus v final prime squared, I'll have v initial squared times sine squared plus cos squared. Sine squared plus cos squared is identically 1. So this is, you can immediately double check that v initial squared is equal to v final squared plus v final prime squared. Okay, so that's that. But now let me sort of give you two, so what you really want to do now is consider two very special cases. Okay, so we're going to run out of room here. Let me erase, say, this little part of it here, and just show you two special extreme cases. And let's try to see whether this makes sense. It's always important when you get a final result, you're not done. You want to look at it and just think about it a little bit and see whether it makes sense, or see whether you learned something new. Okay, that was maybe unexpected. So the two special cases are alpha is equal to 0. So alpha equals 0 means that we want the colored ball to take off straight to the right. So the cue ball is coming in, the colored ball comes out. So it's really a one-dimensional collision. So it should reduce to our previous result for a one-dimensional collision. So in this case, the initial situation was we had the cue ball coming in with some velocity to the right, and the colored ball was at rest. And the angle at which the colored ball takes off is supposed to be 0, it's supposed to take off in that direction. So the final situation is this colored ball takes off with some velocity to the right, and the cue ball is at rest. So this is rest, and this is rest. So let's just see whether that's what we get. Everything's flying all over the place here. Okay, so this is in fact when alpha is equal to 0, what this equation says is that v final, the final speed of the cue ball, is sine of 0 is 0. So the final speed of the cue ball is rest. So it's coming in with some speed, and then it just very quickly, during the very short time of the collision, comes exactly to rest. So that's right. And then v final prime, the speed of the white ball, it should take off at the same speed as the cue ball originally had. And so when we stick in alpha equals 0 degrees in here, cosine of 0 is 1, and v final prime, the speed of the white ball, is equal to v initial, the initial speed of the cue ball. So that's correct. So our two-dimensional perfectly elastic collision reduces to the expected results in one dimension. Okay, when it's a head-on collision like that, and when the masses are equal. Okay, and then the other case, interesting case to look at, is when the angle alpha approaches 90 degrees. Okay, so what does that mean? That means what you want to do is you want the white ball to come and just barely give a glancing collision with the colored ball. And so the white ball is basically going to continue to move in its original direction with its original velocity. And this colored ball is going to go off at, say, nearly 90 degrees. Of course, you can't make it go off at exactly 90 degrees because then the velocity will be 0, but nearly 90 degrees. Okay, so let's look at that situation. So now we have a cue ball moving in to the right with some initial speed v initial, and we've chosen it so that it's a glancing collision. Okay, it's going to hit that white ball initially at rest. Okay, and so we're going to try to make that angle nearly 90 degrees. So in the final collision, what we expect, just sort of common sense wise, what we expect is, because it's a very slightly glancing blow, we expect that after the collision is over, we expect the white ball, the cue ball, to be moving off to the right with almost exactly the same speed as it had before. And we expect this colored ball to be going off, the colored ball here. Let me draw it just, well, okay, just after the collision. The colored ball over here will be moving with very small velocity, approximately equal to 0, and at approximately 90 degrees. Okay, so let's just check if our formula here reduces to this expectation when alpha approaches 90 degrees. Okay, so when alpha approaches 90 degrees, sine of 90 is equal to 1, and so the final speed of the white ball is equal to the initial speed. Okay, so it just takes off like this. And the final speed of the colored ball is cosine of 90 degrees is 0, and so the final speed of the colored ball is nearly at rest. Okay, and so there's very little kinetic energy in that final ball. It just moves very, very slowly down at nearly 90 degrees. Very little kinetic energy. All of the kinetic energy, virtually all of it, is still in the white ball, so it's moving with the same speed and in the same, basically the same direction that it had before. Okay, so that's nice. So it's always nice to take your final result and look at extreme cases and see whether they make sense. Okay, so this is an example of a two-dimensional collision. There are no general formulas. What you do is you just apply, in that particular situation, you apply conservation of energy, which is one equation, conservation of momentum, which is two equations. You just write everything out. And then you add this other condition, this additional condition, which tells you something about the nature of the collision, in this case, elastic. And then you just solve it. And then when you're done, you sort of check whether the answer makes sense. So this is a great example of a perfectly elastic collision in two dimensions.